L'Hopital's rule only works on fractions. With other indeterminate forms, like exponents, what we do is use algebra to turn it into an indeterminate fraction, and then we're able to use L'Hopital's rule. In this video, we'll talk about how we use algebra on indeterminate exponential limits. As a reminder, the indeterminate exponents are infinity to the 0, 0 to the 0, and 1 to the infinity. For example, the limit as x goes to 0 of log x to the x. That's log x is going to negative infinity and x is going to 0. This is a reminder that when we talk about indeterminate forms, we don't distinguish positive and negative infinity. When we say indeterminate form of type infinity to the 0, negative infinity still counts. Limit as x goes to 0 of x to the x is an indeterminate form of type 0 to the 0. And 1 plus 1 over x to the x is an indeterminate form of type 1 to the infinity, as x is going to infinity. This is an important example, the book does it, because this comes up when calculating compound interest. A typical example, what is the limit as x goes to 0 from the right of cosine x to the 1 over x squared? The limit as x goes to 0 of cosine x is cosine 0, because this is a continuous function. Cosine 0 is 1. The limit as x goes to 0 of 1 over x squared is plus infinity. So this is an indeterminate form of type 1 to the infinity. So we expect to use the technique that I'm about to show you. Now we use something we use a lot. In fact, we use it so much that I hope you're going to look at it and go, oh yeah, that's the obvious thing we always do in this situation. We want to get rid of this exponent, so we take what we had and we go e to the ln of the same thing. So so this limit is equal to e to the ln of the same limit. And these are equal because e and ln are inverses. We haven't changed it. We've just written the same thing a different way. And this is what we often do with exponents. We replace them with e to the ln. We are allowed to swap the order of ln and the limit. E to the ln of the limit is e to the limit of ln. This is because ln is continuous. Any continuous function we're allowed to do this with. Pull it in and out of a limit. This is something we covered briefly way back in section 2.6. And now we've gotten to the point, which is this exponent is inside a logarithm, so we can use the logarithm rules. We use the logarithm rule for exponents to pull the 1 over x squared out in front of the logarithm. 1 over x squared times log of cosine. By the way, notice that I just keep this e to the limit. It just keeps following us through every step and we're leaving it alone, but we're writing it every step so we don't forget it. Now we have 1 over x times log cosine x. I'll sort of belabor this and say this is a product. Log of cosine x, well, as x is going to 0, cosine x is going to 1, so log of cosine x is going to 0. And 1 over x squared, well, as x is going to 0, that's going to infinity. So this is an indeterminate form of type infinity times 0. Whenever you use this technique on an indeterminate exponent, going to e to the ln of the thing, and then pulling the exponent down using log rules, you'll always end up with an indeterminate form of type infinity times 0. Then we do what we always do with indeterminate forms of infinity times 0. We find a way to write them as a fraction. In this case, it's really easy. That x is on the bottom, and log cosine x is on the top. So e to the limit as x goes to 0 from the right, log cosine x over x squared. Now we have a fraction. The top is going to 0. We already observed that. The bottom, as x goes to 0, x squared goes to 0. This is an indeterminate form of type 0 over 0, so we can try to use L'Hopital's rule. We take the derivative of the top. The derivative of the top is 1 over cosine x times negative sine x. The derivative of the bottom is 2x. Almost always after using L'Hopital's rule, we should rearrange the fraction we get. We don't want to just blindly apply L'Hopital's rule again. Especially, we should combine those denominators. So we have a negative 1/2 times a 1 over cosine x. There's a cosine x in the bottom. That x is in the bottom, and the sine x is on the top. negative a half 1 over cosine x sine x over x. We could apply L'Hopital's rule again. There'd be nothing wrong with that. You'd get to the right answer. But we might notice a shortcut, which is we might notice that we can use the limit laws to break this into pieces we know. We can use the constant multiple rule to pull the negative 1/2 out. And we might notice that 1 over cosine x and sine x over x are two limits that we independently know. So we can use the limit law for products to say this is the limit as x goes to 0 of 1 over cosine x times the limit of sine x over x. 1 over cosine x is continuous at 0. We just plug in the 0. It's 1 over 1, which is 1. Sine x over x is a limit we're supposed to recognize. That could easily mean that you have the value written down somewhere, but you want to recognize sine x over x as x goes to 0. That's a limit you know. It's equal to 1. So this is e to the negative a half times 1 times 1, and that's equal to e to the negative 1/2. You could then rewrite this as 1 over square root e, which is the same thing, but actually e to the negative 1/2 is a better way to leave it, because that's more likely to be useful if we do something else with the number later. It's a really common mistake to lose track of that e to the whatever somewhere in the process. I just write it down every step. It's just one extra letter, and it makes it a lot less likely you'll make a mistake. One way or another, don't forget, you've got to have that e to the thing at the end when you're using this technique. The main thing to note is this very first step, replacing the limit with e to the log of the limit. Because after that, all the steps should be the natural things you expect to do. The only tricky part is pulling out this e to the log thing at the beginning. And by now, that's something you should be used to, because again, this is something we do a lot when we encounter exponents and want to do algebra with them. One more example. What is the limit as x goes to e from the right of log x to the 1 over x minus e? As x goes to e from the right, log of x is log of e, which is 1. 1 over x minus e is going to positive infinity, because the denominator is going to 0 and is positive because x is a little bit bigger than e, because it's approaching from the right. So this is again an indeterminate form of type 1 to the infinity, so we expect to use the same technique we used on the previous one. I'm going to write the technique slightly differently this time. This is an alternate way to write it. It gets us to exactly the same place. This time we're going to say y equals the limit as x approaches e of log x to the 1 over x minus e. And now we'll take the logarithm of both sides. So we'll say log y equals log of limit of log x to the 1 over x minus e. And again, using the continuity of logarithm, that's equal to the limit of log x to the 1 over x minus e. If you prefer, you can do this the way we did the previous one. Instead of having this log y thing, you could just say we're talking about e to the limit of log x to the 1 over x minus e. And you'd get to the same place in the end. These are both good ways to do it. The only reason I'm showing the second one is because a lot of students seem to prefer it, because you don't have to keep writing e to the whatever every step, and that's fine as long as you're careful, and as long as you remember to write both sides of the equation. This is something I keep mentioning, that usually we have equations and they have two sides. We shouldn't just write formulas all by themselves. So if we don't want to have to write e to the whatever every step, we really need to keep track of we're saying y equals the limit that we started with, and right now we're talking about log y. Now we proceed as before. We use the log rule to bring down the exponent. This is the limit of log x over x minus e. That's times 1 over x minus e. That's an indeterminate form of type 0 over 0. By L'Hopital's rule, we can take the derivative of the top and bottom. The derivative of the top is 1 over x log x. The derivative of the bottom is 1. So this is the limit of 1 over x log x. That's continuous. You can plug in e. 1 over e log e. That's 1 over e. But log y is 1 over e. We have to remember where we started, the left side of our equation. Log y is 1 over e. Y is equal to e to the log y, which is e to the 1 over e.